My goal in this video is to talk about plots of temperature versus heat, and then a lot of students get asked questions about temperature versus time as well. Let's get into it, and let's start with this one because I think this makes the most sense, and then we'll go into this one. So forget this for now. All right, so imagine you have some material and you're measuring its temperature as you heat it up. So let's say we know the amount of heat we put in units of joules. So maybe you have, I don't know, a hot water bath and you're able to take that heat energy, or a space heater, and heat up something. You might expect something to first be in the solid form, then in the liquid form, and then in the gas form. And so what we see here is there's going to be a slope while it's heating up to the freezing point or the melting point. Then it's going to melt. The temperature won't change. This is a latent heat. Then it's going to turn all the way into a liquid and start heating up until it reaches the boiling point. And then there's going to be a phase change, and then it's going to be a gas. So now in this case, let's try and understand what these things mean. So I'm going to start with this term because that one's probably the easiest. Here we have something that's being heated, positive heat, Q is positive. We expect this to be positive mass times the latent heat of fusion, or vapor of fusion in this case. So notice increments on this axis have units of joules, so that should be a heat. Similarly, we could go to this one. Here I'm heating up the liquid. Maybe I should do this in red, huh? Well, whatever, it's too late now. Maybe you're green-red colorblind, and this is the one case that works out great. We're going to get Q equals mc delta T. We're going to assume our approximation is valid, that C is constant over this entire temperature range. Not always true, but whatever. Okay, so in this case, when you see slopes, I want you to think of delta T's, right? The temperature's changing. When you see zero slope, that's a latent heat or a phase change. So that's the first thing, all right? Now, what are the units on this particular slope? So, here, just to be clear, we're at the boiling or condensation. So this is positive in this case because we're heating it up. It'd be negative if the curve was going downwards. This would be M, L, V for vaporization. All right, positive because we're heating it up. The graph's going this way. All right, so in this case, what is the slope? In particular, let's look at the units of the slope, right? Or, well, let's just do it. It's rise over run. Rise is delta T, and run is the amount of Q you put in. Now, you could be saying, shouldn't you use delta Q? I'm just going to put Q right now, because Q itself is a transfer, so it's a change in heat. I don't know. You should strictly be using delta Q here, but I'm going to use Q to make this make sense. Notice if I rearrange this a little bit, if I say Q equals 1 over slope times delta T, Q up here, 1 over slope there, this looks kind of familiar. Notice that 1 over the slope is probably MC. So if I rearrange this a different way, 1 over the slope of this graph times M should be specific heat, lowercase c. So that's what we see in all of these. Or you could rearrange this and say the slope should be, I guess, 1 over MC. All right. Now, something important to notice. The slopes are not always the same as it changes phase. So the slope, for example, I've got some numbers here. Let's see. For ice, the slope is about 2200 joules per kilogram per Kelvin, which is the same as joules per kilogram per degree Celsius. I can use degrees Celsius because everything in here has a delta T. All right. So for the solid, the slope would basically be 1 over 2200 divided by the mass for ice. For the liquid, it would be, what what is that, 4186. So it'd be 1 over the mass times 1 over 4186, and this one I think is about 1 over 2100, also 1 over the mass. So just because you have, say, water changing phase, do not expect this slope to match this slope to match that slope. That's what I was trying to get at with the numbers. All right, so again, you got your melting points, your latent heats. Your slopes are your specific heats with this weird relationship here. So slope here. All right. And then in this case, what about plots of temperature versus time? Usually they're, in the real world, they're always going to be slightly curvy. And I don't know if they're going to curve this way or they're going to be concave up or concave down. But typically, according to Newton's law of cooling, the object will change temperature most rapidly when the temperature difference is as large as possible. If you put something outside, if you put something in a negative 20 degree freezer, it will freeze more rapidly than if it's in a negative 1 degree freezer, right? Because they're larger temperature difference. So as a result, you get these curvy plots. We're going to completely ignore that for this class and probably will in your class too until you're doing something more advanced. So basically, we assume that the heat will be transferred at a constant rate. So R is that constant rate. Let's get the units of this. So heat is energy, that's joules. This should be joules per second times seconds. Notice how important it is. I guess I should probably put the units on here. Say Kelvin here. Remember, you can use Kelvin and degrees Celsius interchangeably for these particular plots. So the slope in this case would be degrees Celsius over seconds. But now if you take slope times the mass divide by R, you get this, which is not going to fit on the page. Not going to fit on the page. 1 over C. Let me make sure that's all on there. Yeah, okay. So when you're looking at plots of temperature versus time, there's basically a conversion factor. The time can be given by Q over the rate. So you could get back to what we're doing if you know the rate at which things are being heated. But the slopes will ultimately relate to 1 over specific heat. And that's kind of the big thing. The more specific heat you have, the harder it is to heat something up, the more gentle the slope. If water has a huge value of C, so water has this gentle slope. Aluminum, which was only 900, 1 over 900 is a lot steeper than 1 over 4186. That's enough on that.